All right. So it's my pleasure to introduce Timour here. Timour is he studied with my professor in Sweden. He did that after I was left that group and joined IBM and worked on databases there. But then he came and visited at IBM, so we got to know each other quite well there. His self-description says that he started doing databases when he was like 3 years old or something, or later on maybe. So I think that's the treat of people doing databases. They do a lot of databases one way or another, and I think everything is a database. Um, but not many people get as far as looking into a query engine and actually modifying that and trying to improve it. So this is what Timour is going to talk about, the architecture of a MySQL query engine and how things work inside, under the covers. And I think this is going to be quite interesting. So the floor is yours.
Okay. Thank you, Jonas. So, uh, so my talk consists of three parts. The last one being very short one. In the first part, I will talk about the basic principles in our MySQL query engine. And I'll cover two main issues. The first one is how query plans look like and how they're being executed, and the second part is how actually we get to execute. How do we look for good execution plans? And in the second part, depending on time, I will try to cover six of the six most important features that our team developed since and introduced since version 5.0, and one of these features is in version 5.1. And finally, I will talk about the latest stuff we're working on currently, which is either in design phase or already partly implemented. So we begin with query plans and their execution. And first, I will go through the architecture of the query engine. Excuse me. Well, the way a client application talks to the query server is similar to any other database system. You can send your SQL via either ODBC, JDBC, or native interface, or anything you like. Then it goes through the parser. The parser analyzes the syntax. It produces a parse tree. And then a number of the subsequent phases operate on this parse tree. The next phase is the preprocessor, and it does semantic checking, name resolution, and access rights checks. And this is basically where we check whether the query is semantically correct according to the SQL standard. I will not be talking anymore about these two components. Next, the parse tree gets into the optimizer, and it does some logical transformations. It does some cost-based optimization. And finally, some plan refinement. I call this plan refinement because we do not generate P code. So normally it would be called here plan generation, but I use this more general term. Once we get query execution plan, optimized query execution plan, we send it to the query execution engine, which can use a number of data access methods like table scan, index scan, range, and ref or EQRef for the ones who know the MySQL terminology. And it's also here where we compute different join methods. One of them is already here, of all kinds of variants of nested loop join, and currently I'm working on hash join. And the query execution engine, through the handler API, basically this is our term for storage manager API. It goes and accesses the database through through different storage engines. So here I've put three of them, but there are many others already existing for our system. Now, how do query execution plans look like in MySQL? For those familiar with database textbooks, they would know the typical representation of query plans as trees. And the general representation of a query plan is as a bushy plan. That means a tree where the input of a join can be an intermediate result like this one, an intermediate result of a previous join. Both operands can be intermediate results, and this is called the Bushy plan. Well, we don't have that in MySQL. What we have in MySQL are only left deep linear trees. This is our internal representation of query plans. So always the right input of a join is a base table, eventually accessed through some index. Now, given that this is on abstract level, this is the representation of query plans, I will explain more. I will talk more about how they are internally represented. Yeah, thank you.
Is that a strong motivation for why people are using left deep linear trees, or is that just, I mean, is that a limitation or is that a feature?
Well, both. Now the question was, is this a limitation or is this a feature, and was there a good reason for designing it this way? Now my first answer is that actually it wasn't me who designed it that way. So for me this is a fact, and that was designed. It was designed this way from the very beginning. Now the second, the other answer is that generally from database theory it is known that if one does not explore parallelism, which we don't do currently, bushy plans have very little use otherwise. So most of the good plans, so to say, can be found in the space of left deep linear plans. Bushy plans are most useful if you can explore parallelism and compute. Let me go back. And if you could compute each of these two joins in parallel, then it makes sense really to explore this space. But if you cannot do that, then it doesn't make sense really, because the space for all possible plans becomes much bigger, and the potential to get a better plan is not very big. I mean, in simple terms, right? So in order to explain a little bit more how query plans look like, and in the rest of the presentation, I will use a small world database example. So suppose we have 3 tables with a number of indexes on each of them. Each of these tables has a primary key like ID, code, and country, I think. No, yeah, one of these two. Country language is the primary key here. And let's consider this query on the table's languages, a join between languages, country, and city. How would this query actually be represented as a plan? So given that our plans are left deep linear trees, we don't need to represent them as trees. What we do is we represent them as arrays of operators. And the reason I've shown here the operators top down and not bottom up as in the tree is because I would like to make a relationship between how a plan is abstractly internally represented and the explain output of the query engine. So whenever you actually do explain on the previous query, you will get 3 rows, each of them describing in some way each of these nodes in the plan. So I call these nodes plan operators. And for example, let's consider the first one. This is not all the information in the plan operator, but this is the most important. So each plan operator contains the table being accessed, the condition used to access that table, and the condition used actually to filter rows at this level of the plan, the access method being used to access data from that table, and eventually, if there is any index, the index used and the condition used to access the index, right? So, and the same for the remaining operators. So these conditions here are called push-down conditions. So if this is the first operator, the push-down condition is still a select condition, but any other condition below in the plan after the first one can be a joint condition as well. And another important thing to notice is that each of these plan operators has one variable attached to it, which describes the state of the current row. And the collection of these variables, altogether collected, constitute the current state of the pipeline. So our execution is pipelined. We do not materialize intermediate results in general. except for certain cases like block nested loop join or hash join, then we would materialize only some parts. But on a general level, we do have pipelined execution. And again, on the general level, for the simplest case when you have just a nested loop join or index nested loop join, the way it works is you would basically execute this plan via 3 nested loops. Of course, we do not unroll them as such, but just for simplicity, I showed the 3 nested loops. So basically, in this case, for each variable here, row city, we would do an index range access method. We would retrieve we would perform a lookup with this predicate for the first key in the index that that fulfills this condition, and we will load the first key in variable row city here. Then we would, inside the outer loop, we will move on to the next loop. We would use another access method here. It's indexRef, that is direct key lookup into the other index. We will load the second record here. We do the same for the next operator. And once we are complete with all operators, the contents of each of the 3 rows essentially constitutes one result row, and we are ready to return it to the client. And then we move back to the first operator, and we move to the next iteration of the outermost loop, and so on until we retrieve all tuples in the result set of this join. So that's how generally MySQL works. Now, just as a hint, there is one data structure that corresponds to a plan node, but there are also many other data structures that are interrelated with this one. This one is called, okay, I'll say that later on. So there are a number of other structures related, linked to this structure that altogether constitute a complete execution plan. So it is not very easy to find the plan in the source code, the representation of a plan in the source code. Now, how do we, the next couple of slides, I will talk how do we actually get to optimal plans with this representation. Now, the first thing is when one talks about query optimization is what is the cost model. It is slightly more complicated than what is on this slide, but generally, as in all other databases, cost is proportional to disk access. And the cost unit currently is equal to 1 random read of a data page, which is just a constant, which is not necessarily realistic. The only thing that we care about is to be able to order plans properly. And the main cost factors in MySQL are data statistics. So we take into account the number of pages per table or per index. We take into account cardinality of tables and indices. We know the length of rows and keys, even though quite imprecisely. There is no special statistics on that. We just do, if we have variable length columns, we could just have to do some guesswork there. There is no special statistics on that. We also have key distribution. So because I've discussed that with Jonas, and he said, like, in some cases you get really bad plans. Sometimes the problem is if you don't have an index on a table and you happen to use non-index columns, there is no statistics on those. So the only thing we know is the number of rows and data pages if there is no index. So there we have to do quite a lot of guesswork, unfortunately. But we are going to fix that next year sometime. And another set of information we use is schema information. So that's whether a column is unique or not, whether it's a primary key or not, and whether the column is a given column is nullable or not. And the simplified cost model, this is pretty much by the textbook. So the cost of one access is proportional to the number of pages. The cost of join is proportional to the number of pages of the left table plus times the rows of the left table, the number of pages in the right one. And in general, we also do include CPU cost, which is the disk access cost, basically the cost of computing one simple predicate as equality or inequality comparison is some constant defined in the code, is the one disk access divided by some constant in the code. So Now, first we go with MySQL for many years gets exhaustive search, and the search is performed bottom up. So we start with one table plans, and then we gradually expand these plans with bigger and bigger. We add more and more tables. And this is performed in depth first search with a depth first search procedure. And of course, while we do search the space of all possible plans, we use the principle of optimality to prune those intermediate plans which are more expensive than the current best plan. And we also, there is also some rather convoluted heuristics which is possible currently to switch off and on that uses some heuristics on key access. It's kind of hard to explain in few words, but it's there, so it also prunes some of the plans as well. So the overall, the general phases of the optimizer there are 4 general phases. We begin with a number of logical transformations where we do like traditional things like negation, elimination, conversion of outer to inner joins, equality and constant propagation. We also have a couple of tricks to evaluate tables that happen to be single row tables. So if we can determine that a certain table access will give us one single row, then we can retrieve that row already at optimization time, bind the constants of that row to the corresponding variables, and then use a constant propagation and eliminate eventually some predicates. So this is a very neat trick. I haven't seen actually that in other databases. Maybe Jonas knows. Then once we do all these logical transformations, we have a phase that prepares for cost-based optimization, and basically this phase extracts. Yeah, sorry, I didn't see you.
On the single row result, can that apply if you can tell that even though the table has more than one row, that you're going to get just one result?
Yeah, the question was, if we have a table that contains more than one row, are we able to predict whether a table actually whether the query will actually get exactly one row? Yes, for example, if there is a primary key and we happen to have equality conditions on the primary key, we are sure that there will be exactly one row in this case. We prefetch it during query optimization, and then we bind all the constants. We use constant propagation. So we may actually deduce already at query compilation time that this query will return nothing. Right? Other cases are also nullability when we know that some column is null, cannot be null. And if we use the predicate is null, right? So we know there is nothing there already. So no need. Yeah. Sorry, this. Yes, it does the single row replacement execute exist in 4.0? The answer is yes. It is quite old. I don't know, maybe even in 3 something. I'm not sure. Yes. So the question is the table locked before query optimization? Right? Yeah, it is locked. I think so, actually. Jay, do you know when tables are locked? Yeah, the answer is that tables are locked upon access. But the thing is, perhaps when, you know what, I have to check this. When it comes to single table access, I'm not sure what, like this constant table replacement, I'm not sure what happens. Perhaps logically one should think that the table should be locked and then released only in the end. But I have to check this out. Yes?
Slightly different way to ask that question is if the table handler estimates that it's going to get one row, is that sufficient, or do you require a constraint?
The question was, does the table handler...
Hey, there's only one row for this predicate.
Yeah, does the
Unique
table,
constraint.
yeah, the question is, does the table handler selectivity estimate already tell us whether there is one row? In some cases, depending on the table handler, yes. For example, my ISAM, it may return, it returns exact row count. But if it's InnoDB, we don't know.
But if my ISAM says there's one row, but you don't have a unique constraint, so you
Well,
can't.
we use it. We trust my ISAM that there is one row, and we will use this algorithm.
Do you trust all the table handlers?
No, there is a special flag internally that tells us whether, well, the implementer of the table handler has to provide, there is a special flag that it should set. So the optimizer checks whether a particular table handler returns exact row counts or not. And then it will accordingly apply this. For example, if the table handler supports MVCC, like InnoDB or the upcoming Falcon engine, I actually don't know about Falcon, but InnoDB for sure does not return exact row counts. So we cannot trust it. Okay, I'll go ahead. So this preparation for cost-based optimization phase, actually I'm also not aware of if other systems are doing it. What we do here is that from all the where clause, we extract a subcondition whenever possible, which is a conjunction of all equality predicates. And it is internally it's a graph of all these predicates. And basically on all of the arcs of these graphs, we assign the fan out of each of the conditions. And this allows later on, basically this is the input to the optimizer to estimate the selectivity of conditions. So that's one of the things that is probably both disadvantage and advantage. During query optimization, we do not use all conditions of the where clause to estimate to estimate the number of rows in the intermediate results. What we use the result of this preparation phase and the pre-estimation of the equality condition fan out only. So the next phase is cost-based optimization, which uses one very important component, the range optimizer. Unfortunately, I don't have time to describe. It's worth a whole talk on its own. It's a very interesting component that we use in many cases. Basically, this is the component that takes some a Boolean formula of range conditions and figures out the minimal sequence of intervals that represents this where clause. Then we have the condition pushdown phase. So once we have a complete plan and we know the order of the tables in the plan, we can decide what condition can be executed where. And then we have a so-called like code generation phase. It essentially sets function pointers because we do not generate P code. Now, the second part, in the second part, I will speak about the new features from 5.0. So, as a logical continuation from the previous part, the next thing I'll talk about is the greedy join optimizer. So, the cost of optimization can be pretty high, as probably some of you know. If you happen to need to optimize more than queries with more than 10 tables, it may easily take hours or even weeks in some cases, right? So exhaustive search is not feasible for such cases, and all modern database systems do have other search algorithms except for the exhaustive one. And that was my first task at MySQL. I implemented a greedy search algorithm. And the idea of this algorithm is that it allows you, it is not fixed, so to say, it allows you to control the depth of the exhaustiveness, which we call search depth. And the general ideas are that at each search step, whenever we consider how to continue a partial plan, we estimate the potential extension only to certain depths. So basically, we do not run a full exhaustive search. We pick the best extension based on this prediction step, I call it. And that's why we call it a greedy algorithm, because it picks the best current possible extension. We forget all other extensions, and then we continue, we extend the plan, continue with the next one. So the most important thing to know is that there is a trade-off. We can get worse plans, but we get them faster, much faster. I will show one graph in the end, so I did some measurements of this. Now, this is a visual representation of the algorithm. So suppose we start with an empty plan, and on the next step, we want to pick the first table in the plan. So the way we do it, we go through each of the tables, and in this particular case, I have to make the image smaller, I use the minimal possible depth. So suppose we look just one step further. Basically, the idea is we extend each plan of one table with all possible other tables. And we estimate the cost. Suppose that of all these extensions, the plan with the minimum cost is T3 and T2. And then we say, okay, our first table is T3 because it has the best possible extension with depth only 1. So we select our plan, initial plan to be T3. And then for T3, we do the same. For T3, we continue and perform exactly the same step. So instead of having a very wide tree here going through almost every branch, basically in this case, we will consider very few combinations. In this case, the complexity of this search procedure is quadratic, so it's very quick. But this depth here, it can be controlled. So you can make, it is possible to control how many prediction steps we do, the optimizer does. There is a user variable for this, system variable for this. And so generally, there are several ways you can control the optimizer. You can control what indexes are selected. Like use index, this hint would tell that please use only this index if possible. Force index says use this index even if table scan is faster. And ignore index means exclude those particular indices. Yes?
Are we now after things that are in 4.1, et cetera, or some of these?
These are actually, the question was whether these are index control features are available at 4.1. Yes, they are available in 4.1. But for completeness, I just made a slide how all possible ways to control the optimizer. Now, these are new features from 5.0. And the first one is degree of exhaustiveness. This is basically a way to control what I just described, the greedy optimizer. 0 means automatic, so the variable is called optimizer search depth. 0 means automatic, so there is a small procedure, currently rather dumb, that decides what would be the search depth. 1 is minimal, as on the previous slide. 62 is maximal. And anything in between is okay. Of course, if the depth is bigger than the number of tables, it will be exhaustive anyway, because the search, it cannot search more. The depth is no bigger than the number of tables, right? And there is another variable which is called optimizer prune level, and this is the magic thing that I will not describe here, probably because I don't understand it very well, actually. I admit it. I mean, it's a very strange thing. If somebody is interested, I can show it where it is. It's just one if condition. And there is the third thing also available in the older versions is the straight join hint. And with this hint, you can force a particular join order. And then you just directly bypass the join optimizer. This is a small graph showing like what is the trade-off between what the depth, the search depth, and the time it takes to optimize a query. Of course, this is on a synthetic set of queries, so other queries may show different results, but it is quite representative. So no surprise, I use here exponential axis because otherwise it won't fit. So as one may expect, the curves are generally, the dependency is exponential, but I run this on a number of different machines just to see on modern architecture approximately how much it takes to optimize on our, with MySQL's optimizer. And basically it seems that a good cutoff value is 7, and that's what automatic means currently. It just checks whether your query has more than 7 tables. If it has more than 7 tables, it sets the depth to 7 and no more, because we know that even if the user didn't do it manually, probably it's going to take a very long time. For example, 10 tables. 10 tables take up to 100 seconds, so probably nobody wants to wait. 15 tables, that's going to be a very long time. So that's why I decided to set it to 7. Now I'm switching to other new things in the query engine. So these are mostly, yes, sorry. Sorry.
Do you have blank hash?
Do we have planned hash?
Cache.
Cache. Yes, there is something called query cache, and it just compares. The question was, do we have planned cache? The answer is yes, we do, and it called the query cache, and it only contains. No, planned cache. Oh, sorry, I got the question. No, we don't. So what happens is when you do a prepare, you will run the optimizer every time. Even if when you do execute, you will run this thing, the optimizer every time. Yeah. Arjen wants to add something.
Of course, we have the query cache, and the query cache actually skips that entire step. The query cache stores the original query, just in plain text, and the result set. So for an identical query, you get your result. And generally, you do that for smaller queries, but you can do it for bigger queries. It is, provided you have memory for it, and provided you tune it properly, way faster than just storing a plan. Storing a plan still means you need to do the retrieval. And this is just a step beyond. It's simpler, but it's highly effective.
Okay, Jay will add something else.
There's one thing about that, just a slight thing. When Arjen said that it's the plain text of the query, something a little bit different. It actually MD5s the query. So even one space difference in the select statement, one little space, that's a different query, okay? So it MD5s it, to store it in the query cache. So make sure that you're not like adding different comments every time you put in a select statement, because it's gonna be a different query to the query cache. So.
Yeah, that's how I initially understood the question, that it was about the query cache. But in terms of plan cache, no, we partly there are some parts which we do not redo every time when you do execute, but particularly the join optimizer is called every time, for a number of reasons which I can explain later on. So the next thing I'll talk about is a new index access method called index merge. It was implemented by one of my colleagues. And the index merge uses it's very much based on the range optimizer. So this is the component that takes a where clause and generates a minimal set of sequence of intervals that represents this this where clause. And this is also used in the current range for generating the currently existing range access methods already existing for 1. So let me first remind you how does it work, how range index scans work in up to and including 4.1. Suppose you have this query with range predicates. It will go through the range optimizer, among other things. We get a set of sequence of intervals. These intervals are shipped to the query execution. And then the handlers can accept in some internal representation sequences of intervals. And then basically the handler will retrieve all the rows in each of the intervals. Given that we have a let's say, B-tree index, this is quite efficient way to scan an index. Now the problem comes when you do have an disjunction of two conditions, but each of the conditions can use a different index. There is no index for both together. So what we did for this case is 3 different algorithms that can efficiently use both of the indexes and compute the result of the overall result. So in this case, we have an equality condition on one index, on the index country, and a range condition on another index. So what we can do in this case is that we can just use 2 range scans on both indexes and collect the row IDs of each of the 2 resulting keys and put them in a intermediate storage that computes only the unique values of the row IDs. Once we are ready with both index scans performed in sequence, we can continue and either and retrieve the actual rows. There are two other cases when we can do even better than this. There are two cases when we can even avoid this intermediate storage. If it happens so that the row IDs on the two indexes, we know that they are ordered, we can do something better. For example, if we have a disjunction, and this method is called union index merge. If you have a disjunction, we can just start from the index containing the smaller row IDs. Basically, we check the first row IDs of both indexes, and we continue with the one with the smaller ones. We continue until we reach, like on step 1, until we reach a row ID that is just smaller or equal than the row ID in the right index. If we get a bigger one, we switch to the right index, and so on. So basically, this is the same algorithm as the merge step of sort merge, exactly the same. And this allows us to produce the result by using two indexes in a streamed manner without any intermediate materialization. We perform a similar algorithm for conjunction. So basically, we just do the opposite. We collect row IDs from both indexes until they are the same. Then we skip all the others. Then we collect the other row IDs until they are the same. So we do this in parallel on both indexes, and we're in the end, once we finish with both indexes, we can just actually on each step we can return already one complete row in the result in this way. So this is fully pipelined, and there is no need for any intermediate storage. And finally, we can also, the optimizer also automatically does index superposition. So we can use these methods, we can combine these methods to compute, to merge indexes on more complex conditions. And there are some internal limitations of the range optimizer, but generally speaking, this index merge superposition is applicable to almost any Boolean expression of range conditions, such that all range conditions are covered by some index. And then we can compose them in such a way. Because if we know, especially if we know that the output of an intersection is also ordered by row IDs, we can apply also the row ID algorithm to do the union. And we can superimpose in such a way the previous algorithms. So this is the basic idea behind index merge. Yeah.
Can I do index merge if my predicates are joined predicates?
No, because the question was if it is possible to do index merge on joint predicates. The answer is no. At least I already got this question yesterday. I can't think of an easy way to do that, because the whole idea here is that we have row IDs, and row IDs happen to be unique only per table. So I just don't. You see, that's the whole point.
But if I'm joining, if I've already joined tables A and B, the next table I'm going to join over is C, and I have joined predicates where, you know, A dot column equals C dot column and B dot column equals C dot column. Presumably, I could come up with the list of row IDs. I could. There are sort of two index lookups into C, and I can come up with a list of row IDs and merge them.
Well, but still, the whole trick of merging two sequence. I mean, we're basically merging row IDs over the same table. And the thing is that we know that if we pick or skip one particular row ID, in this way we identify the row. I don't see how can this be done for two different tables. You see, because if we have row ID 35, let's say they're integers. If you have row ID 35 in one table and row ID 35 in another table, they are actually identifying different tuples. So we can't do anything with that.
That's not my question. Maybe I'll come up at the end and
yeah. Well, maybe you'll give us a good idea. I don't know. Now, the next thing, this is something I implemented for 5.0, is an algorithm that we call loose index scan. It's a special access method for group by and distinct queries with minimum and maximum. This is, for the ones familiar with Oracle, this is a subset of what Oracle calls index skip scan. So basically, this is a method that allows you to use an index even if you don't have constants forming a prefix on the index. And here is how it generally works. Suppose we have this simple group by query that has a maximum aggregate function in addition to that. And suppose we have an index in this on the fields country, name, population in this order. And we have group by on the first column. We have an equality predicate on the second column, and we have our minimum or maximum on the third column. So in version 4.1, what we could do, the only thing we do is actually we do just a simple index scan. Basically, we jump and we check each and every single key in the index. But in 5.0, we do something smarter. So what we do is we first jump and we identify, suppose I started here somewhere in the middle of the index, but we do this step for every group in the index. So what we do is we first find the first row in a group. For example, we start with the first key in the index. We don't know what's inside it, but we can retrieve it. So we get the first one. Then we look, what is the value in the column country, the group column? Well, it's USA. And since we know that this is an ordered index, we know that all subsequent tuples, all subsequent keys contain exactly the same value in this column. We use this fact later on. So given that we now have an equality condition, we want some constant, we can add it to the constant USA, and we form a new search tuple. And now we can immediately jump and find the tuple USA Sorrento, for example, in this case, right? So we don't need to do a scan to find that tuple anymore. And since this is the first tuple with this value and the index is ordered, we know that 290 is actually the minimum value here. But the query needs maximum, so we have to do one extra step. We actually go and here I did not display that, but we look for, there is the handler API allows one to look for the next tuple after the tuple beginning with some value, with some constant. So we jump to the first key of the next group, and then we know that exactly the tuple before it, which is the last tuple in our group. So this is the tuple USA Sorrento 1260. In this way, we can get the maximum value in just 3 lookups instead of doing an index scan. And if it was, if we were looking for the minimum value, we would need 2 lookups per group. If we just need to find the group, we do 1 lookup only, right? So this, since group distinct is equivalent to group by, we apply the same trick for distinct queries. And I heard from customers, some customers got up to 100 times performance improvement. It was really nice. And there are some rules of thumb. The logic of this access method is exactly the opposite. So if you're designing your indexes, the logic is the opposite as you would do for range access methods. There, you need the most selective index. Here, you need the least selective index, because the bigger the groups, the fewer the jumps, right? If you have only one big group, you will do 3 jumps per whole table. If you have smaller groups, you have more jumps. If your groups are just one, if you have a unique index, this basically doesn't give you anything, because it is the same as doing an index scan. And the general rules to apply this method is that the index must cover all fields in this order. First, you have the group by fields, equality condition fields, range access method fields, and then in the end, minimum and maximum fields. And all these fields have to be covered by the index. So 5 minutes. 10. 10 more to go? Now, the next thing is partition pruning. That's a new feature from 5.1. The problem is that how many of you know that MySQL has partitioning in general, table partitioning, except Jonas? And okay, so MySQL does have table partitioning since version 5.1. Yeah. 5.1.7 says. Okay, anyways, 5.1 something. We do have table partitioning, and it is pretty much done by the standard. So for the ones familiar with table partitioning, on syntactical level, it is the same. Now, what we did in the optimizer group is we added a feature that allows one to to logically already at compilation at compilation time to figure out that it is possible not to access certain partitions. And we call that partition pruning. So the problem we're solving is given a query over some partition table and given the DDL that describes the partitioning. For example, we have a range partitioning, and we match the DDL and the where clause, and we find a subset of all partitions that that actually need to be accessed, and we throw away the partitions that do not need to be accessed. So there is a small example here. Suppose we have a hash partitioning on column department number, and there are 4 partitions. That basically, in this case, we would use the modulo function to compute the hash. And if you have the query select star from EMP where department number is 1 or 2, one can see that essentially we don't need to access 2 of the partitions because we already know that this query will need only 2 partitions to test. It is not possible to find the result in any of the other partitions. And if you do an explain partitions on this statement, you will see the result is that actually only 2 partitions remain, P1 and P2. And how this happens? We first, that's a bit, this is actually a bit tricky to explain. Okay, I'll give it a try. So now what we do is, we create a virtual table definition from the partitioning description. So basically, we pick all the fields specified in the partition, and internally we create kind of a virtual table description. And then we use the range optimizer, which can analyze range conditions over any table. So we pick the where clause with its range conditions, and we pick this virtual table, and we feed them to the range optimizer. As a result, we get a sequence of ranges. And so this is a very good case of reuse of one of our smartest components. And once we get this interval sequence, we walk over the interval sequence and over the partitions, which are essentially ranges as well, and we perform logically an intersection of those, and we throw away the partitions that have empty intersection with the range sequence, with the ranges in the range sequence. So visually described, suppose we have one range of many ranges. Suppose it's from 1 to 5. Well, let's say it's the range AB. There can be many ranges. So this is what happens for one range. We pick this range, and we run all the partitions and compare each one, the boundaries of each one with the range. And if the range does not overlap with the partition, we throw that partition away. Yeah, okay. So this is the general idea of partition pruning. Now, there is some more about the internals, which I will skip for lack of time. I will just mention that we do have equality propagation, as most other databases do. I suppose like database people are quite familiar with this, so I will skip this. The benefits of this is that we can generate automatically more conditions to use for index access. We also use this for equijoin transitive closures, so we can deduce more join equality join conditions. We can generate more predicates to use for range index access. And we also have some new features related to nested outer joins. So basically, we can we have a very unique thing. Unlike Firebird and Postgres, in MySQL, if you have nested outer joins, the intermediate results of the nested joins are not materialized. We have fully pipelined execution, so nothing is materialized, and I think that's quite unique. Probably commercial databases have that as well. I'll ask Jonas again later on. And we also do transform outer joins into inner joins whenever there are no rejecting predicates on the inner table. So if we know that there cannot be a null, we just transform the outer join into an inner join. And this allows us this expands the search space for the optimizer, so it can actually explore more different join orders. And finally, what's coming soon? Some of these things, some of these features will make it in 5.2, some will not. I do not make any promises specifically. So the major feature that has been asked for a long time from the optimizer team is subquery optimizations. And what we'll do is we will apply subquery optimization to subqueries in the where clause, typically in, exists, and similar subqueries, and we will flatten them through semi-joins. And in the cases when this cannot be done, for example, if the subquery contains group by, has a group by, then we will use hash semi-joins to efficiently compute in predicates and equality predicates. We have another access method, new access method, which is called batched multi-read range, which I will not describe now, but basically it is able to process many range predicates in a batch, and it reduces, for example, for NDB cluster, it reduces network access time. And another big feature, this is something I'm working on, is hash join. Currently, it will be implemented through so-called one-pass algorithm. Basically, if a table being cached doesn't fit in main memory, we will not partition it. We will just not apply hash join. The next step would be to also partition tables bigger than join memory available. And finally, we will implement also loose index scan, which is similar as Oracle's index skip scan. We will implement it for more general cases with equality conditions. And that concludes my talk. I hope it was interesting. Questions?